Welcome back to the video. Uh, Now we are going to solve a problem on Prestressed Composite section. So let's get started. Okay. Just take a while to read out the problem clearly. Pause the video. I'm not going to read it for you. I'm straight going into the problem. Okay. So as the problem is given, first you have to determine the section properties. First you can do the area. 100 is the width and 200 is the depth of the prestressed precast member, and then we have calculated here the section modulus, that is Vt square by 6. Now coming to the prestressing force, initial prestressing force is given as 150 kilonewton, so obviously it's taken. Now one important thing is you have to read here, that is the beam is prestressed by tendons with their centroids coinciding with the bottom curve. So what does it actually mean? So this bottom curve term refers to one particular condition uh, where you can see in this diagram that the tensile stress is not at all present. That is, you can say the top fiber is at zero stress, right? So this particular situation of where the top fiber is being at zero stress and no tension being developed, the position of the tendon is then referred as bottom curve. So it has a specific value, like you can calculate the value at which the tendon is located, right? So I'll ask you to do one thing, you can derive that value. So at what depth the tendon is being located, uh, such that there will be zero tensile stress, right? Or the top fiber is under zero stress. So you do that. Uh, so due to that, if you derive, you will find that the stresses due to prestressing force, it comes around 2p by a. So if my tendon is at bottom curve, the compressive stress will be 2p by a, right? So if you calculate, it comes around 15 Newton per millimeter square at the bottom and 0 at the top fiber, right? So this 15 at bottom and 0 at top fiber. Now this is initial stress. So in the problem it is given that 15% loss is there. So obviously effective stress will be 0.85 into 15, that is 12.8 Newton per millimeter square. So if you see the diagram, 15 initial stress, effective stress in both cases 12.8. Okay. Now self weight of the precast beam, the dimension is there, like with depth multiplied with the unit weight. So that way you get the self weight of the precast beam. And due to that self weight, you have a moment. How to calculate? Obviously WL square by 8. Span is of 5 meter. So WL square by 2 do, and that you get the self weight movement. Now due to that self weight movement, you can directly calculate the bending stresses, that is, this is the moment and this is the z, that is section modulus, m by z you are doing, so z that you calculated here. Okay, so this is for the section only, 2.25, that is precast section. See, only for the precast section you have calculate the bending stresses, 2.25 negative, 2.25 positive. Now comes the self weight of the in situ cast slab. Obviously the dimension is given, 40 mm is the thickness and 400 mm is the width, and multiplied with the unit weight of concrete, and then you calculate the moment same way you calculate it in the last case, right? And then you can directly calculate. Now there is two things in case of propped, unpropped, due to the self weight of the slab, the pre-stressed member does all the work, it takes all the stresses, where in case of propped section, the whole composite section will take the stress. So we have not calculated the Z or I for the whole section, right? We have calculated only for the pre-stressed member. So for now, we will just calculate the for the unpropped section, and the stress is due to that m by z again 1.8, and you can see it is written as 1.8. Now the remaining stresses that we have to calculate all are having, you see, both the section are participating, the slab and the pre-stressed section. So for that we need to calculate the section properties of the composite section. So here what you can do, you can use the like the formula a1 y1 plus a2 y2 equals to ay, and y you can take about certain reference point that they have taken as top fiber, right? And accordingly they have not shown the calculation, but accordingly they have found out that distance of the centroid of the composite section from the top fiber is 87 millimeter, right? And again they have found the second moment of area for the overall section. So if you're having challenge to find that, please look after these things like how to calculate moment of inertia of composite section in Google, you'll find. Then from that you can find the section modulus. It is different? Because it's a composite section. Obviously ZT means section modulus with respect to top fiber, right? So since the neutral axis is not at a symmetrical depth, so obviously Z we know I by Y. So in case of ZT, it's I by YT. That means from the neutral axis to the top fiber. YT is neutral axis to the top fiber. And when you are calculating ZB, I by YB, that is YB means neutral axis to the bottom fiber. So that way you calculate ZT and ZB, and then the problem becomes very easy. Like you simply calculate the live load that is given in the problem, live load moment you calculate, and at top you do the same thing m by z. While applying z, you make sure when you are calculating at top you are applying zt, and when you're using finding the bottom stress you are using zb. So 4.45, 7.85, you see 4.45, 7.85, right? Now you're considering the propped condition again. To find this thing like 1.8 you have found in case of unpropped, you have to find in case of propped condition. So same moment you are using, right? 1200 Newton meter, and multiplied with obviously 10 to the power 3 to make it Newton millimeter, and then applying ZT at top and ZB at bottom, and find the respective stresses 0.53 and 0.94. See, 0.53 and 0.94, and finally when you add all of them up, you get a resultant stress diagram like this. So this is all about the problem. It's very easy. In the description you will find a PDF file, and you go through that, and there will be certain assignments. I hope you do that and submit it over mail. Okay, thank you. See you in the next video on design of steel structure.